We are literally getting down to the last 4 lectures, although we'll have an optional one in RRR week, I think. We'll talk a little bit more about that, but welcome back. So just briefly from last time, if you remember, we talked about how transactions can intersect with file systems in a wide variety of places. Basically, the ACID semantics of transactions are quite useful. Atomicity, consistency, isolation, durability were all properties we talked about. Probably the most important one that's always present is atomicity, which basically says that either everything happens or nothing happens, and durability, which says that once you've committed it, it actually does happen. It actually is durable and doesn't get lost under a wide variety of circumstances. The issues of consistency and isolation, there are many varieties of these, and so weakened semantics often show up in commercial databases and so on because it's really hard to get all 4 of these properties at once. Consistency basically being that the database is never in an inconsistent state with respect to committed transactions, and isolation means that one transaction will never see the uncommitted results of another. So, were there any questions on this? Pretty much transactional ideas show up everywhere in operating systems and systems in general. And, it's all about how well can you get the ACID semantics and what's the impact on performance, basically. So we are spiraling our way out. Today we're really going to dive into distributed systems, and our last topic kind of for the last week is going to be reliability, security, and the cloud. But for now, I want to go back to this picture which we've seen before, which is really treating the world as a huge parallel system. And if you think about it, we've got the Googles of the world up here, or the Amazons, or the big cloud providers, and then we have big machine rooms that are kind of owned by companies, and then as we move our way down, we go all the way down to little tiny devices and the Internet of Things, and this scale from the really tiny to the really large is all tied together, typically in one network that allows routing between all these components. So in a very real sense, this is one huge distributed system. And so we can talk about it that way by sort of considering the semantics of such systems. And before we get there, let's sort of say what's the difference between centralized versus distributed. Centralized system is kind of what we've been really focusing on a lot so far, where all the major functions are kind of performed by one server, perhaps, and there may be multiple things accessing that server, but pretty much the functionality is centralized. And, client-server model is something we can talk about, and we will in a little bit, but this tends to be considered a centralized version. When we get to peer-to-peer, we're getting into sort of the extreme end of the distributed system range. In this case, you have many computers all kind of working together, and peer-to-peer in this instance means that every one of them are peers of the other, and there is really no centralized server. And pretty much systems of interest that we are going to talk about for the rest of the term span the range from here, kind of at the centralized, to the distributed version. Okay? Everywhere, of course, is a network of some sort. So why would we want to have something very distributed? Okay, like on the far right there. So oftentimes it's much cheaper to build something out of lots of simpler components and tie them together with a network than to try to build one really big thing. And oftentimes in this sort of the extreme version of this, these machines are all owned by individuals and they happen to be collaborating together to do something. So BitTorrent. Anybody here use BitTorrent? Okay. Anybody use any other peer-to-peer systems? Do we have anybody on the dark net in here? Oh, you probably shouldn't tell us that. So onion routing, right? There's lots of interesting systems out there. The attraction there is really that if they're cheap, you can have your own resources that you're tying together, okay? And often collaboration's a lot easier in this big distributed sense because In the centralized server case, you often have to have a single account, or everybody has to have an account on that one server, and so there's some manager that you have to talk to get an account before you can do anything, whereas in this distributed sense, oftentimes you can just work without having a central account. So there's a lot of kind of advantages there. The promise of these systems is higher availability, better durability, more security. And the reason for that is higher availability, there's more components that can be up. Better durability, you can put data everywhere and therefore it's durable. More security, well, each piece is smaller and maybe easier to secure. Okay, so the question really is, does this promise come out in practice? What do you think? Are these systems more available? Yes, but maybe not functioning properly, right? So what was the difference there? That was the difference between available and actually providing some sort of useful service. We talked about reliability as sort of a goal. Availability is not it. What about durable? Yeah, I suppose, except oftentimes in the extreme peer-to-peer case, you have no control over those machines, and so people might do arbitrary things to them, like erase all their data. You have no control over whether that's going to happen. So that durability one's a little dicey, maybe. And then the more security, well, that's probably never true, right? Because the more components there are, the more chance for somebody to break into one. And so that promise of security usually is not borne out. And the reality is really much more disappointing than the potential. And what I like is I love this quote from Lamport. It says, "A distributed system is one where I can do work. I can't do work because some machine I've never heard of isn't working." Okay, that's my favorite distributed systems quote. And of course, coordination between all these elements gets complicated. And so one of the things we'll talk about next time, we're not going to get to it this time, is we're going to talk about sort of what I would call the peer-to-peer revolution that happened in the early 2000s that led to things like BitTorrent and so on, where people figured out how to scale coordination in a way to use thousands of machines to do something useful. Okay, and we'll talk about some of the peer-to-peer systems that got developed in academia. So going on for a moment here, so our goals of distributed systems really have to be that they're somehow transparent to the user. And what does that really mean? It means that it ought not to be extraordinarily complicated to use a system that just happens to be composed of 1,000 elements because, what if it now has 2,000 elements or 4,000 elements? It just can't be too complicated to use, and it's good to have an interface there that you can give to the user that lets them ignore the scale somehow. And some possible levels of transparency here might be location. You can't really tell where the resources are located, and that's okay. Migration, the resources can move around without the user knowing about it, possibly to optimize things like performance or durability. You might want to be able to have replication happen transparently so that, you store some data, but then somebody else replicates it for you so it becomes durable without work on your part. You'd like to have concurrency in there so that you don't really have to know how many users there are in order to use the system. You'd like to have parallelism, so you can actually use the resources to get some performance if it's possible. You'd like to have fault tolerance, so that when that one component goes down, as Lamport says, you can still use the system. And basically making all this work together obviously requires some sort of communication or network underneath, and we're going to start by talking about the network, and then we'll work into some of the protocols involved. Yeah, question? It's transparent in the sense that the user is doesn't typically have to understand that this is a huge distributed system as opposed to a local system. So the difference between the two is transparent to the user. So it's transparency from a programmer's standpoint, not I know what's going on entirely in the background. You'd like the API to be sort of one that doesn't require you to know a lot about the system. Because if you think about a system that's got 1,000 or let's say 1 million components in it, if you had to be aware of all 1 million components somehow in your use of the system, it probably would be unusable right? So that's the sense I mean transparency here. It's transparent to the user whether it's 1,000 or 1,000,000 nodes. You shouldn't have to know the difference. Question? Yeah.
So are you saying that it's okay?
What's okay?
There's some opaque boundary between the user and this complicated thing behind it.
That's the goal, is that there's a boundary. The goal of transparency is opaqueness. Okay, fine. Okay. All right. The goal of transparency is opaqueness. We'll remember that. Okay. So let's talk for a moment about protocols here. So what is a protocol? So a protocol is an agreement on how to communicate. So for instance, it includes a syntax for that communication and semantics for what the communication actually means. And good protocols are described somewhat formally by state machines. Okay, so it's often represented as some sort of message transaction diagram. Receive this message, go to this state, send out another one. Okay? Now, in human interactions, you guys are used to protocols all the time, but they're much more kind of implicit, like on the telephone. You know, you pick up the phone, you listen for a dial tone or see if you have service. You dial the number, you sort of hear ringing, you hope. Somebody says, hello, and you say, hi, it's John, or Kubi, or my favorite is, hi, it's me. Well, that's a useful thing to say to somebody, right? But there is a protocol for making a connection with a remote person verbally over the phone, right? And now we can kind of get to well, here's why I'm calling. This is the message part of my protocol. So I did the connection part for the first 6 steps, and now I say, hey, do you think da-da-da-da, right? And what happens is the callee now goes into the response phase saying, yeah, da-da-da. And now, at that point, we can shut the thing down by, we say, okay, bye. Callee says goodbye. We hang up. Okay? And so there's several little sub-pieces here, like this is setting up the connection, this is actually answering a message response, and this is shutting down the connection. Okay? So everybody's familiar with this, right? Maybe you're not familiar with the notion of a dial tone, given that everybody uses smartphones today, but this is something you used to get on cell phones. So, other protocols like, how do you ask a question? You raise your hand and you wait to be called on. That's a protocol. Or you wait for the speaker to pause and you yell something out, right? So those are protocols that you're used to. An interesting protocol, which we'll talk about in a moment, is everybody starts talking at once. How well does that protocol work? Depends on who's the loudest speaker, right? Okay. We'll have to solve that problem because that one's hard when there aren't humans in the loop. So let's define a few things here. So an end system is a computer on the net of some sort. So that can be everything from a standard desktop to phones to pads to whatever. We're going to call these hosts in general, but they're things that are connected somehow to the network. And if you remember from the very first couple of days, we talked about namespaces in this domain for hosts, like a host name, which is this sort of www.ecs.berkeley.edu domain name format. We talked about IP addresses, which are basically a numeric routing destination, and we'll also talk a little bit about how you go from host name to IP address in just a second. You had to do that. And then there's the port number, which in addition to the IP address sort of says what class of service. So these hosts that we're talking about here adhere to some namespace, and we're going to have to be aware of the namespace as we go forward. In fact, if you remember, in writing code like this, we basically had this thing in red where we turned a domain name into an IP address by calling getHostByName. Okay, so this was a translation service to go from one to the other. Okay, so what are clients and servers? So a client is typically running on an end host that's sort of at the leaves of the network. It requests service like a web browser. It sends a message to a remote host of some sort. Okay, so this remote host typically has a well-known name and port number and well-known IP address, and so we basically do a get to it. And later it might respond with a result like, sites under construction, didn't get anything back. But the difference between client and server here is a little fuzzy in many instances. In this instance, the client is the one that initiates the conversation. The server is usually the one that's serving the conversation. Okay? Those two can be reversed sometimes in the same situation, and then you get much more like a peer-to-peer analysis here. Okay, so client is often a sometimes on sort of device. It can be turned off at will. The server is usually an always-on thing. Why is that? Because the client's initiating to the server. The client chooses when to start the conversation. The server has to be there to receive the conversation. Okay? So the client initiates the request, etc. Okay? Questions? Fairly straightforward. Now, peer-to-peer communication is often in its extreme. There's no always-on server at the center of it all. And hosts can come and go at will and change addresses, change names, etc. So if you think about this, what's involved in making a system, a peer-to-peer system, reliable? How do you make a system like this reliable? Yeah. So if there are a lot of people using it, that just means there's a lot of systems bouncing up and down. It doesn't mean the system itself as a whole is reliable. Yeah. So redundancy seems like an important starting point. But let's go back to what I was saying earlier. I want to look like I've got a service, like I'm able to get videos or store data or whatever in this big system. Certainly redundancy is important because hosts are bouncing around, but what else is important somehow? Yeah. Establishing communication when, for instance, I don't even know who to communicate with because people are bouncing around and being up and down, right? What else has to happen? I have to transparently be able to deal with a host that I was about to talk to going away, right? So there's a whole new level of reliability here that's kind of interesting. In the client-server case, the client initiates, and there's really no assumption that the server could go down at any time. Question? Yeah. So you're starting to design a protocol for reliability. Sure. So the problem with having a host that's about to go down forward traffic is that usually things go down because they crash or the power goes out or whatever, and you really don't have enough time to set that up. But that's a good thought. We'll actually talk about a type of peer-to-peer network next time, or maybe the time after, we'll see, that will show you kind of some examples of how we can do sort of what you're thinking. But we can't rely on the guy who's going down to do the forwarding. We have to rely on noticing that they're down and doing something else. Okay? Good. So example, peer-to-peer file sharing is the one that everybody likes to talk about. How to share files among 1 million people, or some people used to like to say how to steal music off of the internet, right? That used to be what people thought of as peer-to-peer. And pretty much any host can request files or send files or query to find out where a file is located. And the key is going to be about routing the queries when we finally get there, because the things that we're routing through might be up or down, okay? And we get scalability because as we put millions of peers to work, we can now handle maybe millions of queries because there's as much resource growing as users are growing. Okay, and in this instance, each peer is acting as both a client and a server. Okay? So does everybody see the kind of the distinction? When we get into the peer-to-peer realm, it's like a whole nother animal, right? There's more service, there's more computers involved, there's less reliability, there's huge scaling of requests, and somehow making that work as a coordinated system is kind of a really interesting problem. And we'll give you a little taste for that next time. Okay? Questions? All right. So the problem in all of this, starting kind of at the lowest level here, is that there's so many applications we could come up with, email, web, peer-to-peer, pick your favorite. So many different network styles and technologies. There's wireless and wired and optical and ATM and this and that and the other thing. Lots of hardware. And the question really is, how do we organize this mess and do something useful? And the problem is also kind of shown by this. We've got lots of types of media on the bottom and lots of applications on the top. And the real question is, does every application have to be designed differently for every type of media? What do you think? Okay. Hopefully you've been listening to me long enough this term to realize that if the answer to that is yes, we've got a problem, right? The answer can't possibly be yes. So what do we do instead? Well, the internet avoids this. By the way, this was more and more things here. Sorry, my things are screwed up here a little bit on my animation. But obviously we have layers, okay? Layers of abstraction. And so we're going to introduce intermediate layers that are going to provide all sorts of abstractions that we can use to basically connect applications on the one hand and media on the other. And it's going to be this narrow waist in the middle of what? IP. That's really going to allow this to happen. Okay, how many people here have taken one of the networking classes? Good. A few of you. How many people have not taken a networking class? More of you. Okay. So for those of you that have taken a networking class, you'll have to bear with me a little bit in this lecture. So let's be very basic. What's a network? It's a physical connection that allows two computers to communicate. By the way, we're going to get much more interesting than basic networking at the end of the lecture, so stick around. So what's a packet? So a packet is typically a unit of transfer, which is a sequence of bits with a header that sort of says where it's going. And networks carry packets from one place to another. Okay, and then finally a protocol, as we've been applying at the beginning of the lecture here, was an agreement between two parties as to how information is supposed to be transmitted. And so that agreement is crucial when you've got something like a machine communicating with another machine, because they're really, what do you do if your protocol mismatches? Things just don't work. Okay, so when you really sit down and talk about a networking situation, you've got to know what your protocol is, crucially. Okay, question? So, all right. So now let's do some administrivia. So midterm 2 is a week from today. It's at 6:30 to 9:30 in Dwinelle, 145 or 55, and we're going to put out on Piazza how to map you to rooms. And in principle, all topics from midterm 1 up to next Monday are going to be included. And I would say you should assume, since the address translation, TLBs, and paging discussion was sort of right on the edge of midterm 1, that there's some chance that there will be topics on those areas. And then here's the other things we had: I/O subsystems, storage layers, disks, performance and queuing theory, file systems, distributed systems, TCP/IP, and RPC is going to be today. And then potentially we're going to be talking about NFS, AFS, and key value stores next time. So these are potentially fair game. But all right. Now, closed book, 1 page of notes both sides. You're welcome to bring your notes from last time. I'm not so sure they would help. But the other thing is, for the final, you get 2 pages of notes both sides. So if you want to keep your pages, you could bring those to the final, or you could write brand new ones, up to you. And the last thing I wanted to say about the midterm 2 is there will be a review session in 306 Soda on Sunday from 4 to 6. Okay, are there any questions on the midterm? Yeah.
So the midterm will generally not cover things that were on midterm 1?
Generally not. Yeah, things around the edge of midterm 1 would be in there, but we're not going to put stuff that's from the beginning of the term. You get to be retested on that in the final. Yay. I heard people excited about that. I know you want to do a synchronization problem, but we won't make you do a really complicated one this time. We'll save that for the final. Just kidding. Other questions? Okay, so the last thing I wanted to mention a little bit about, and I'll turn it over here, is there is an experiment going on with some new collaborative video annotation software. Why don't you say a little bit briefly? Why don't you use the microphone?
My name is Dennis. I'm also in this class. I built something called Lectio. It's basically a lecture watching tool. It's a discussion platform for lecture watching. It was built for 61B, basically to solve the problem of when you're watching webcasts, there's not really an outlet for you to ask questions. So you can go on Lectio and sign up and then watch 162 lectures. 70 lectures are also on there, but I think most of you have taken 70 at this point. So yeah, check it out. Thank you.
Yeah, and I understand that this is particularly useful when you actually post questions and answer questions. It's part of the annotation, I think, actually can be queued onto parts of the video, right, as to actual spots in the video. So it's an experiment to see whether this makes watching 162 videos much more exciting, since, of course, you don't have my wonderful face on those videos. You only have the screen, and so I could imagine that it's much slower. But, okay. All right. Are we good on administrivia? All right. And yeah, try this out, because if you guys like this, maybe we'll do this from the beginning of the term next term. I don't know. Who knows? It's an experiment. Okay, so let's talk about networking. So I wanted to start talking about broadcast networks for a second. So shared communication medium, where lots of things are sharing. For instance, a bus is a good example of a broadcast media where you have a processor and I/O devices and memory all plugged into the same set of wires. And the upside of this is that when one thing like the processor is talking, everybody can listen. So that's a pretty cheap broadcast media. Believe it or not, way back when, in research labs, what used to happen was that you would have Ethernet cables that actually went around in little tracks to all of the different offices, and there was a single drop that came down, and you plug that into your computer. And these were all shared media, okay? So when you put some signal in one end, everybody received it. And this is how they did TCP/IP, okay? And what's the obvious issue here? Yeah. Okay, you had a different question. Okay, go for it.
So when something is connected, then it's like broadcasted on the network?
That's right. So this is by nature a broadcast media, okay? And so when you get past a switch, then it becomes point-to-point. But in this particular instance, and this is, by the way, more years ago than I want to admit, everybody who speaks is heard by everybody else. Okay, so what seems like an issue with this? Yeah.
So when one of the cards in one of the hosts goes and starts chattering on the network for no reason, no one can communicate until you find out which host it is and unplug it.
Ah, yes. Well, there is the failure mode problem of too much speaking. What about the normal operation problem of too much speaking? Yeah. No, you're right. Obviously, that's bad. Go ahead. What was that? No privacy. How many people think they have privacy on any network they communicate with? Good. I'm glad nobody raised your hand. Never, ever use Telnet. Okay, because that puts passwords in the clear. Never, ever do unencrypted communication with anything unless you want somebody to monitor you. Okay, so yes, you're right. There's no privacy here, but you don't have privacy now. So, and if you think about Wi-Fi is basically this, right? It's not a cable, but it's every packet you send out is received by every device that's sitting in a given room. So you could set your Wi-Fi card up to hear every conversation that's going on here, and if it's not encrypted, you would hear it. Okay? So the big thing I thought you guys would say right away is, what happens if multiple devices try to talk at the same time? Okay, you get collisions. And so this type of media is great if you want everybody to hear something. So it's great if broadcast is desirable, but it has this problem that when multiple people start talking at the same time, you got to do something. You have to have a protocol to deal with that. Okay? And lots of examples of this kind of broadcast media. All right, so for instance, you've got delivery, you broadcast a packet. How does the receiver know who it's for? So what happens here typically is you send your packet out, and the header says who the destination node is. And even though it's broadcast to everybody, only the node that's looking for the data actually picks it up. Okay, and you can do this in software by examining every incoming packet, or you can set up your hardware to do the right thing. Okay? And most Ethernet cards do this in hardware. All right. So we could build a very complex protocol on top of this if we wanted to, because notice that we can now do a single conversation from ID3 to ID2. It's just that we're broadcasting to everybody in the process. Yes?
So does the operating system like filter through packets it receives?
So that's a good question. Does the operating system do the filtering? So the operating system certainly filters, but you can also set the hardware up to do some filtering for you too. So it is true, though, that if you're in this kind of media, most people, you can set your cards up to be what's called promiscuous mode, where it will receive every packet that comes in, and then your operating system can examine them. Okay? Good. So we could build another protocol on top of this because we have effectively point-to-point protocols on a broadcast media. Okay? Except we effectively have point-to-point protocols on a broadcast media. Okay? Now, questions? Now, I wanted, just because I wanted to say a little bit about this, broadcast media are around a lot these days still, and really we have to have an arbitration of this media, which is the act of negotiating a shared media to deal with the problem of two senders trying to send at the same time. And if you think about it, in a room like this, if two people start talking, one of them just hopefully stops talking long enough for the first one to talk, and then you sort of let the other one talk, hopefully. What happens in a computer-to-computer communication is it's not so clear what to do. Okay, you can easily recognize that you have a collision because you get garbled data out, but then how do you know how long to wait? Okay, so that's a little tricky. And so I wanted to say, back in the 70s, for instance, that's last century, basically, there was a packet radio system set up in Hawaii called the Aloha Network. It was a blind broadcast protocol with a checksum at the end of the packet. So it recognized that there was a failure because when you had two people talk at the same time, the checksum failed. And basically, if you got a bad checksum, you just threw the packet out. And so now the real trick is the sender waits for a while, and if it doesn't get an acknowledgement because the thing was garbled, then it just resends. Okay, so this effectively works because now if two senders try to send at the same time, both get garbled result, and they just send back later. Okay, can you see what we need to do to make this really work, though? What if they... Go ahead. Yeah, so there needs to be some randomization in here. Otherwise, there's just no way this could work, right? And in fact, the problem is really stability as well, because as more and more people start talking, you get more and more collisions to eventually you have no communication that happens, right? And I will say, by the way, that original Ethernet, which is from way back in the 80s, was one of the first practical media, and it used wires instead of radio, but it was still a broadcast media, as I showed you. And the key advance in all of this to making this work was arbitration called CSMA-CD, which is Carrier Sense Multiple Access Collision Detection. So the carrier sense says, don't send unless you don't hear anybody talking. Then you start talking, but you detect collisions because your packet gets trampled. And if so, you abort, wait, and retry. So you sense carriers, so you only start talking if nobody's talking. And then if you start talking anyway and you collide, then you retry. And the back-off scheme, which is crucial, is you choose a wait time before trying again. And the question might be how long to wait after trying to send and failing. And a key thing here is if everybody waits the same amount of time, you got chaos. So there's got to be randomization, right? What happens if you have two people communicating? If you have two people communicating, they start talking. Mostly it works. If you happen to collide, you back off randomly, you communicate. What if four people start communicating? Can anybody sort of give me an idea of back-off time required for four people to communicate versus two? Okay, it's not really square, it goes linearly, but it increases, right? More senders, more back-off. And so the way this actually works typically is it's adaptive randomized waiting, where the first time you pick a random wait time with some initial mean. If you collide again, you pick twice the mean, and so on. And so you basically back off exponentially. And this is where exponential back off first showed up. Okay? And what this does is this automatically adapts to the number of people that are trying to talk, because as more and more people talk, you have more collisions, and you back off more. Question? Yeah.
How is it scale?
So this scales,
Hundreds of millions of people.
well, so first of all, it doesn't scale to hundreds of millions of people. That's clear. What it does do is, in that scenario I told you about with the original Ethernet cables in a ring, you could only have so many drops on the cable before it became a problem. And the real way to look at scaling is kind of what fraction of the bandwidth do you actually get out of this sort of scheme. And as I recall, it's somewhere in the 60 to 70% range.
Because doesn't Wi-Fi use a similar like wireless use a similar kind of collision detection?
Well, there are some wireless schemes that sort of are a little more intelligent in that they actually assign slots. They're sort of a slotted scheme. But yeah, so there are Wi-Fi schemes that are essentially like this. And so you have to get that back off to work well. Okay, questions? So by the way, if you buy a router today that's Ethernet, it really does have all of this stuff in it. You just only make it point-to-point. You never use broadcast anymore. Pretty much. So, why have a shared bus at all? So why not just have point-to-point links, okay? And a point-to-point network is a network where every physical wire is only connected to two computers. So it might look like this, where each computer is connected to a switch, which is then connected to another computer. And if you look at this scenario here, this is pretty common today. You have a switch in your house, and then you have a connection with a router and or internet device that then takes you out into the internet, and everything is point-to-point. And so the nice thing about this is there's no collisions, presumably, between these two endpoints, because these are full duplex connections, and so both can be talking to each other at the same time. All right? So why not always do this? Why were there ever broadcast media? Yeah, go ahead. So broadcast is useful, is your answer. Okay? Why else? But see, clearly broadcast has its uses, but it's also problematic if you're trying to use up all the bandwidth because you get lots of collisions. Yeah?
Because we hadn't invented the algorithm used in like switch networks yet.
Well, it's actually not that we hadn't invented the algorithm for the switch networks. It's really a question of cost. It was expensive to make something like this because you actually had to have a processor that could run at full speed and do MAC recognition and so on to do the right thing. So this was really, switches sort of started showing up when the cost got low. Okay? And the nice thing about modern switches is you could broadcast into this by marking something as a broadcast packet, and the switch will send it to everybody. Or if you do a point-to-point connection, it'll just do point-to-point. So it does the right thing. Okay, it only uses up people's time if they need to be used up. So Internet Protocol, or IP, is kind of the one that survived. Believe it or not, there were lots of protocols at one point, and IP really kind of took over. And as a result, now the Internet's this huge network of computers. And, I forgot to update these numbers. So we are getting up toward the past, close to the 1 billion folks on the public Internet and many more computers after that. So there's lots of things on the Internet. So an IP packet is a network packet on the Internet, not surprisingly. An IP address is still pretty much a 32-bit integer, which tells you what the destination is. Now, there are those of you who are probably going to say, what about IPv6? They talk about IPv6 in the networking classes, or don't they? They do? What did they say about it? It's bigger. Okay, good. Anybody know how many bits are an IPv6 address? 128. What about deployment? Yeah, go ahead, yeah. Little dicey. IPv6 has been the technology of the future for the last 20 years, and it's finally getting to where it's being deployed regularly, okay? I would say, all the new routers we put in and Wi-Fi networks we put in now all handle IPv6, but that's a very recent thing. But let's talk about what's much more common still everywhere is the IPv4 packets, which are 32-bit integers. And you typically see this, a dot notation like this, 169.229.60.83 is an IP address where each of these represents 8 bits. Okay? This is probably like Coeus or one of our file servers in Soda Hall. Actually, I said it's a CS file server. What do you know? So an internet host, remember we talked about a host earlier, is basically a computer connected to the internet. And some of these actually may be connected only through private routers and may not be directly connected. Okay, but we would still probably call it an internet host because it can initiate connections to servers. Any questions on this? By the way, I'll get you the updated numbers on the number of direct connects because this is much higher. I apologize, I didn't update these slides. Okay, so let me say a little bit about subnets. I want to just give you a little terminology since we're taking a little bit of a dive down internet lane here. So a network connecting a set of hosts with a related destination address. So a subnet is a group of hosts that are together physically in some location typically. And with IP, all the addresses in a subnet are related by a prefix of bits. So what we typically say is if it's a /24 network, that means that every host on that network has the first 24 bits the same, and it's only the last ones that change. Okay? And the mask is really which bits do we mask off to identify the subnet. And so if you look, subnet's identified by 32-bit value with the bits which differ set to 0. So here is a subnet inside of Berkeley, 128.32.131.0/24, basically says every host 128.32.131.xx is part of that subnet. Okay, does everybody see the terminology? Question? And by the way, sometimes you write it like this, where you put the mask instead of the /24. Okay, anybody seen this notation before? Probably. Those of you that have taken the networking class. So if you actually set up your own networking equipment, you will become very familiar with things like this. So what's the difference between a subnet and a complete network range is that the subnet's always a subset. Okay. And by the way, in that old scenario I told you about where there was a wire that went around the offices, everything that was in a single broadcast domain was typically the same subnet. That defined a subnet. Okay? Now with switches, it's a little trickier because, for instance, I have a switch that I have at my house that's actually got order 8 subnets all going into the same switch because it's got VLANs on it. Okay, so things are a little trickier today. But in the old days, you could actually have tell what a subnet was because it was a physical wire. Okay. So I did want to say a little bit about address ranges. So it used to be that addresses were defined by class A, B, C. Class A network is one where the first octet is set and the rest of them are part of the subnet. So this is a huge subnet. And what's kind of interesting about this is big organizations got these subnets. So like MIT, all the addresses are 18 dot something, 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 something. It's a /8 network. Berkeley, if you'll notice, actually has 2 /16 networks, 192.168 and 128.32. Okay. And then what you typically get if you're in if you're getting sort of service from an internet provider is you often get either a class C or lower. And these are actual ranges. So this is Huffman encoded. So class A networks, the NN is from 1 to 126. Class B, it's from 128 to 191 in the first part. And then this guy is whatever, and so on. And so organizations used to hand these out, except we're running out of bits. There are just not enough bits in 32 bits for the world. And so now pretty much nothing is quite this organized. And so there are still some organizations that own like Class A networks, but there aren't too many of them because if you think about it, we're tying up 2 to the 24 internet addresses in a vanishingly small space. So, okay. So what's the internet? The internet is a hierarchy. The way we build that is lots of switches. Okay? Not every host is connected to every other host. There is not the switch, okay, that's sitting in the middle of, Nevada somewhere that everybody connects to. That would just be a bad idea. Instead, we've got a whole set of hierarchies here where we have subnets that are served by switches, and then a router is typically something that can know how to deal with different subnets. And so the internet as a whole is a whole series of interconnected routers that all talk to subnets, and the way you get from Berkeley to Beijing is you have to go through a series of hops. First, you route to your default router, and then the router figures out, based on the subnet you're going to, how to get you closer, and then eventually you get to that subnet that's somewhere in Beijing that you're talking to. Okay, so that's the routing process. Question? Yeah. Say that again? Are the routers on a subnet? You know, typically the routers are attached to subnets. Okay, they're pass-through points for subnets. Hosts are on a subnet. Now, what makes this a little tricky is that oftentimes routers serve as having switches on one side and kind of an internet link on the other, and so in that funny sense, you have a box that you get from Comcast or somebody with a bunch of ports you plug into your computer, and on the other side is a cable that takes you to the internet. That thing is both a router and a switch, which means it gets a little confusing as to how you want to think about it. And that box, in that instance, that box is definitely producing a subnet, and you know, the computers that are plugged into it are on a subnet. That answer your question? Yeah. Okay. Any other questions? So I hope you see that this routing... Yeah, go ahead. Yes. 2 switches can communicate with one another. So modern smart switches, you just can take a whole bunch of them and just plug them together. And what happens is they act like a mega switch with lower bandwidth. So they do inter-switch routing protocols that figure out who's all connected to all of the different ports. And so in a good switch today, you can just plug them together, and it's as if you had one big switch. It's just the bandwidth isn't quite as good as if you had one big switch.
Is it possible to have 2 switches communicate with one another, each one representing a different subnet?
So the question is, can you have 2 switches communicating with each other where each of them is talking a different subnet? The answer is much more complicated than I'm going to give you, and you can ask me afterwards. But in general, 2 subnets always need to have a router in the middle. Okay, but you can have router-like functionality inside of switches. This gets really messy with modern smart switches. So, but let's say no. I'm going to answer your question. No, 2 switches need to have a router between them. Okay? Good. So now, by the way, I'm hoping you all see the interesting part of this problem is the hierarchy is obvious because it's needed, but the problem is how do we get from one point to another? Okay, how does that routing situation get set up? Because somehow I know that when I talk to a server, here's a client, I talk to some server over here, somehow my packets get over there and my responses get back, and it's got to work. And I think if next time you go and use a web browser, and you think about where that browser is and marvel a little bit about the fact that somehow your packets get there. Okay, every now and then I pause and I marvel that this works at all. Because there's a huge complexity. Okay, and I think you should marvel. Okay, and sometimes it doesn't. There have been some pretty catastrophic failures of the internet. Like there was a time in the early 2000s where the internet itself was partitioned somewhere in the middle of the U.S., because a single optical fiber went through this tunnel and a truck went in and blew up and melted the fiber and it partitioned the internet. Okay? Now I'll tell you that doesn't happen much anymore, okay? But there were some catastrophic failures of that sort. Okay. So some simple terminology which you've all heard is a local area network is a small geographic area, and here we can get speeds certainly into the gigabit range in Soda Hall, but we can get up into the 40 and 100 gigabit range soon. So we just have new routers we just put in that have 40 and 100 gigabit service. Going to be hard to use that, but they're going to some of the new cloud. We have a new cloud testbed infrastructure. The wide area network, which are those long haul links that go out of Berkeley and elsewhere, are much lower bandwidth. Okay, so you get in the megabits per second, not the gigabits per second. So right off the bat, you're kind of at a loss. When you're communicating within SOTA, you can go really fast, but you go from Soda Hall to Beijing, you're going to get really, your service is going to be much slower, and that's because you're going over slow links. All right. So let's talk about routing. So routing is the process of forwarding packets hop by hop. And you need more than just a destination address. You need a path. How do I get there? And of course, everybody uses post office as an analogy. When you write down a letter, this is a physical piece of mail where you write the address on it. I know you guys probably don't do that anymore, but you can actually still put a stamp on a letter that's addressed somewhere and put it in the mailbox and it will get there. Okay, I'm not sure how long the actual U.S. Post Office is going to be in business. It keeps threatening to go out of business, but the way this works is that address has a zip code on it. That's just part of the process. It goes to your local post office. The local post office forwards it up to another regional post office and so on. It gets sorted, a path is figured out, and eventually it gets to the destination. That's actually kind of impressive that works as well. And the internet routing mechanism is done by routing tables. So every router has a table lookup to decide where the next hop is going to be. And so when a packet comes into a router, what happens is it matches against the routing table and decides which of its ports to go out. Now, as you can imagine, not every router knows about every destination. Instead, the router needs to know how to get a packet closer to the destination. So if you look at this diagram I showed you earlier, here, this subnet may know it's going to Beijing and forward to this router, because that's the only thing it can do. This router may not have any idea about subnets over here. Instead, it may forward on to another router that's more knowledgeable and closer in network space to the destination. Okay. In fact, if you guys take a look, how many have ever actually taken a look at the routing tables on their laptop? A couple of you. You can do that. You should take a look. What you'll see is that most routes from your laptop over Wi-Fi are actually to a default router, which it gets when it gets the address, and that default router is the one that knows how to get closer to your destination. So your laptop has very little routing knowledge at all, just how to go one hop. Okay? All right. So any questions on routing? Now, I will say that these routing tables contain a lot of things. They contain a destination address range and an output link closer to the destination, and local routers don't have very many entries, and routers in the core of the internet have a lot of entries. And the question you might ask is, where do those entries come from? Okay, because the internet is not a stable system. The internet is a bunch of things plugged together that sometimes mostly works. Okay? And so how do you set up these routing tables? So since there's no centralized state in the internet, you need some algorithms that do that. And ideally, you'll have an entry per subnet or portion of the address in the big routing tables. But where do they come from? And the way they come from is there's algorithms that are running constantly in the background acquiring routing table entries. And here's an algorithm you might imagine, right? The routing table has a cost for every destination subnet. And periodically, every neighbor router exchanges their routing tables, and you sort of pick the best entries and you store them in your own routing table. Okay? Is that a good algorithm or a bad algorithm? Okay, why is that a bad algorithm? Okay, so first of all, this is very subject to malicious routers, right? Let's assume for some reason you have a way of getting rid of malicious routers. What else is bad about this? Seems a little... Go ahead, what? Well, it seems a little expensive, right? Because there's a lot of information being exchanged. And this idea of cost is a little tricky. And so in principle, what happens is there's many different scales and many different protocols. So in the core, like at SOTA, whatever, there are protocols that run that have much more exact information. But as you get out into the internet as a whole, there's protocols like BGP and a bunch of these others that actually exchange information. And the other thing that I will point out before we go off this topic is that BGP, the Border Gateway Protocol, is not about finding the shortest path from point A to point B. The Border Gateway Protocol is about A, finding a path, and B, adhering to the various agreements between internet service providers. Okay, and so those agreements may be, well, you're allowed to route video traffic from Berkeley across my networks to this other place, but you're not allowed to route traffic X across that. And so BGP actually has to take into account a whole bunch of policy things as well as actual distances. Okay. Questions? Yeah. Say again? So, service providers own lots of routers. So Comcast has a whole series of routers, as does, other big service providers. Tend to be, AT&T, and there's, the NSF actually used to own a whole bunch of the internet. And so, these routers are all owned by different people. And it's sort of up to BGP to sort of deal with agreements between these different internet service providers as to how to route traffic. Now, BGP, by the way, can occasionally set up loops, and so packets get stuck in loops. All right, and so BGP is not a perfect science, but it mostly works, and so you mostly don't have holes in the internet. Mostly. Okay. So finally, before we take our break, I want to say a little bit about naming. We talked about mapping DNS names to addresses. How do we do this? Well, first of all, we need to do it because very few people like to remember addresses like 128.32.139.48, unless you're really, maybe you're really attached to that IP address because you own a server there or something. But other than that, pretty much you need to do this translation. And so the mechanism for that, of course, is DNS, or the domain name system, domain naming system. And basically the way this works is it's a hierarchical mechanism where you have local name servers, like the Berkeley.edu name server knows about Berkeley items, and there might be an MIT server that knows about MIT items over here. And notice how the Berkeley.edu name service knows how to talk to the EECS.berkeley.edu name service. And so when somebody over here, or somebody tries to talk to, say, www.berkeley.edu or www.eecs.berkeley.edu, there's a hierarchical way for querying. You start by seeing the local cache, and then you work your way up, and eventually, suppose you're in a company, you eventually get to the top level, which says, well, you're trying to do a .edu thing. Okay, here, go to here. Oh, you're looking at berkeley.edu. Okay, talk to this guy. Oh, you're looking for eecs.berkeley.edu. Look at this one. And so there's a hierarchy of queries that actually work here. Okay? And each domain is actually owned by a particular organization, and they're managed by this Internet Corporation for Assigned Numbers and Names, or ICANN. And so you have to go through a whole series of queries. And so you might imagine, and by the way, everything's cached, so if I talk to an address and it has to go through this big query, and then I talk to that address immediately again, I don't have to go through the whole process because the resolution is cached. Okay? What's the challenge here of this service? Yeah. Yeah, so you have to, first of all, if they crash, it may be that we lose whole domains, so that's a problem. So it turns out these are actually replicated. Then you might say, what was the other problem? They're crashed, you want to replace names. I mentioned things are cached. The problem is when you add a new name or you change the IP address of a name, it sometimes takes a while for that name to show up because there's caching throughout DNS. Okay, but there's a much more, go ahead. Caching throughout the DNS system. So how important is it to get the results correct? So if you imagine an attacker manages to route your queries from your bank to somewhere that's not your bank, you start running into problems, okay? And you might say, well, basically there are certificates to take care of that, and we'll talk a little bit about certificates in the last week of class. But in fact, what do you do when you get some error message that says, the certificate date is out of date or something like that? You always say, what was that? Make an exception. Yeah, go for it, right? So this system that's put into place to try to prevent you from getting these kind of weird attacks, everybody ignores, which is kind of too bad. And you might ask the question, is DNS secure? It's definitely a weak link, because what happens if an attacker convinces you that www.wellsfargo.com is their own server instead of the Wells Fargo server, and then they convince you to log into that server. Okay, notice the only thing you're going on is the name. You're not going on the actual IP address because you don't know the IP address. Right? So this is interesting and problematic, and in fact, I don't know how many people have heard of the infamous DNS bug. Okay, in July of 2008, Dan Kaminsky, who was a security researcher, actually discovered an attack that allowed an attacker to take over pretty much everybody, convince everybody who was in a given IP provider that they owned the whole domain, like they owned berkeley.edu, and as a result, any query you made to berkeley.edu would go to one of their servers. Okay? All right, you should look this up. This is it's pretty detailed, but it's basically an attack that goes on this recursive process for DNS by sort of flooding the network with bogus responses until somebody picks it up. You should look this up. What was interesting about this is it was very high profile, highly advertised. You've got to patch DNS, but nobody was told why. We won't tell you. Got to patch it. Got to patch it. Got to patch it. And it was a huge mystery until everybody had, in theory, patched, and then there was security researchers were told what was going on. So this was like, oh my gosh, this is a huge hole. Everybody patch. We're not going to tell you why. You got to patch now. What I mean by patch is everybody has to fix their computers, their servers, their DNS query mechanisms, their DNS servers to basically prevent this attack, which was a huge hole in the DNS protocol. So this was a pretty interesting problem. All right, let's take a break, and we'll come back. All right. Sorry for the short break here, but I want to cover a couple of things here. So let's talk a little bit again about what a protocol is. So we said it's an agreement with two parties as to how information is to be transmitted. So an example is, system calls are the protocol between the operating system and a user in the application. Networking has many levels of protocol. And there's the physical level, which is the actual mechanical and electrical network. There's the link level, which is packet formats. There's the network level, which is network routing and addressing. And then there's things like the transport level, where we're starting to reliably deliver packets. So notice that there are 3 levels at least of abstraction before we ever get to the point where we have packets that are being delivered reliably. And that's because at the lowest level, packet delivery is pretty flaky. Packets get lost through collisions. Packets get lost through transmission errors. Lots of reasons. Okay, so and if you look at today's internet, we have lots of different layers, and you could actually study. There's an OSI layering, which you'll study in your networking class. We're not going to go into that here, but basically at the lowest level here are the different communication mechanisms. And as you move up, we've got the network level, which is IP, and then above that, transport level is a couple of packet types, UDP and TCP, which we'll talk about. And then on top of that is the rest of the applications. All right? So layering is basically building complex services from simpler ones. Okay? So the physical or link layer is pretty limited. Packets in this basically are typically limited to what's called an MTU size, somewhere between 200 and 1,500 bytes total. So that means if you're sending a huge file, you know for a fact that it's going to be lots of little packets at best, okay, because that's just a physical limitation. And our goal in the following is basically to see whether we can go from physical reality, which isn't what we want, into an abstraction of messages, which is much better. So the physical reality is limited size of packets. We'd like to have arbitrary size. The physical reality is that packets can get reordered. We'd like to have ordered packets. Okay, imagine watching that movie if all your frames were reordered. We'd like to go from unreliable packets to reliable messages. From machine-to-machine communication to process-to-process communication. What does that mean? That means when you think about having two things communicating with each other, two physical devices, you really want some process to communicate with some other process, not a machine to a machine. Okay? And then, of course, in reality, packets can only be routed over a wire, so that's local area network, but we want to route them from here to Beijing or here to Europe or something. Packets are asynchronous in reality. Maybe we want a synchronous abstraction. And packets are insecure, and we'd like security. So pretty much we have a lot of work going for us because the physical level here isn't great. Okay? And the way we build a good message service is we just build it up. So how do we handle arbitrary size messages? We chop them up into little pieces and send the pieces. Okay? That one's probably almost too obvious to say, but the important thing to note is that we're going to have to reassemble our big messages at the destination. And if they're out of order, we're going to have to reassemble them in order. Okay? And the IP protocol is basically something which finds a way to send packets to an arbitrary destination in the network, but these packets are of fixed size or smaller. In other words, they're of 1,500 bytes or smaller. And they're unreliable, so messages can be lost. And basically, we have to somehow route those limited-sized packets, but route them anywhere. So that's what IP provides you, the ability to take datagrams of a small size and route them anywhere in the network. And what's interesting, if you haven't done any networking, is that IP really has 256 possible protocols. So TCP IP is only one of 256 protocols. Okay, there's UDP IP. When you do pings, that's ICMP. So there's a lot of interesting protocols here, and you study those in a networking class. We're going to talk about a couple of them. One of my favorites is IPsec, which is an encrypted packet format that you use for doing VPNs. But here's the format of an IP header. I know you all wanted to see what an IP header looks like. There you go. So every IP packet has these bytes at the beginning of it. And if you notice, here's IP version 4. Okay, this is 20 bytes total. There's a 32-bit source address and 32-bit destination address in the header, as you can imagine. And then there's a bunch of other things, like this protocol here is the thing that says that it's TCP/IP instead of just UDP/IP or something else. Okay. Any questions on the header? You could study this just by doing a Wikipedia entry if you like. So how do we build a service out of this? Well, if we want to do process-to-process communication, we can use IP to route things from machine to machine, but now we don't really want to go from machine to machine. We want to go to actual processes on those machines, and that's where ports come into play. So the port space is a 16-bit identifiers at the source and destination, which you've run into. We talked about them on Lecture 4 when we talked about the well-known port 80 for, what is that one for? Yeah, for the web, right? And what's 443? HTTPS. Very good. So the ports are in addition to the IP addresses. That's the part that identifies what actual service or process you're going to go. And if you remember, we said that a communication channel is uniquely defined by 5 items: a source address, a source port, a destination address, a destination port, and a protocol, where that protocol is that little 256-bit thing I mentioned, okay? And UDP, for instance, is the unreliable datagram protocols actually wrapped on top of IP and gives you a process-to-process communication. So the 20 bytes at the top are the header for IP, and to it we add 2 ports, a source and destination port, and some checksums and a length, and then we wrap the data in that, and now we've got a basic datagram service that can go from process to process. Okay? And this is extremely low overhead, and oftentimes UDP is used for high bandwidth video streams, etc. You can use it very antisocially because it doesn't have any way to slow you down if you're overusing bandwidth. Okay, so, but it's a nice, clean, stripped-down protocol, and it's protocol 17. Okay. So how do we get ordered messages? So, well, they arrive out of order. What do? Because it's packet-based, so what you do is something. So here's, for instance, just to let you know, so packet 0, packet 1 might be the way you transmit it, and packet 1, packet 0 is the way they received, and what do? Okay, you queue onto them, you queue them on the destination, and you reorder them. Okay, but how do you reorder them? Yeah, sequence numbers, right. So ordered messages on top of 100 ordered ones, we assign sequence numbers, clearly. Good. And so at the destination, you say, well, I got, packet number 3 before number 2. You hold on to it, you reorder. Okay. Question? Yeah.
So UDP doesn't have sequence numbers?
No. UDP is an unsequenced protocol. If you wanted to have sequence numbers for some reason, you'd have to add those into the data.
So how does that work if you're getting processing data and you need to reconstruct something? How does that work if you don't know?
So it's a good question. What do you do with UDP if you need to reorder packets? Oftentimes you don't. So, or go ahead. What were you going to say?
Doesn't that happen in the application layer in terms of UDP? Most applications just add it on top.
So there's 2 answers to this question. One is if you want it, you add it and have to reorder them yourself, but the network layer doesn't do it. The second answer, which is probably more likely, is UDP tends to be used for multimedia things where data loss is expected, and what you often do is you deal with a reordered packet by dropping a frame because maybe your video, you wouldn't really notice it anyway. So UDP is used in lots of ways that don't actually require sequencing, and so if you want it, you got to add it yourself. So sequence numbers are very specific to a particular connection, and reordering among connections normally doesn't matter. So if you have 2 streams of video to 2 different video players, it doesn't matter what order those packets arrive in because they're totally separate streams. Okay? So the way we get reliable message delivery is what? Well, we send a packet, but it doesn't make it. What do we have to do? Yeah, we have to acknowledge so that we know to retransmit. Good. So physical media may lose packets. Congestion may lose packets. So if all of the packets are going through Kansas, it may be that they're no longer in Kansas because they've been dropped on the floor. Okay? So the problem with congestion is the default thing to do on the internet is you just drop the packets. And so that's a reason you might lose packets. Okay? And often this is a rate mismatch where you're sending things too fast and the routers can't handle them. And we're not probably going to quite get... Yeah, go ahead.
Isn't there a mechanism for the receivers that I want you to send at this speed? I thought like one of the protocols had that.
Yeah. So we haven't quite gotten there. We'll get there, I guess, next time. But that's one of the crucial things about TCP/IP is that it adapts the sending window to deal with congestion. Okay? Good question. So anyway, the way we get reliable delivery on top of unreliable packets is we have to basically acknowledge, but the challenge here is we want every packet received at least once and only once. Okay, and that second part there is a little tricky because it could be that I send the message, it gets received, it's acknowledged, but the acknowledgement is lost, and so I send it again. Okay, so in an unreliable network, you've got a problem that you may be duplicating packets without knowing as well. And of course, the sequence numbers can help you there a little bit too. And we basically are going to combine ordering and reliable delivery with a single sequence mechanism typically. And so using acknowledgments basically looks as follows. So A sends a packet, B acknowledges, that's great. If there's a timeout because A sent the packet, it got lost, it'll send it again, and eventually you get an ACK. So that seems like a way to get reliable delivery. But some questions that come up is, well, if the sender doesn't get an ACK, does that mean that the receiver did not get the message? Yes or no? How many people think it does not mean that the original message was not delivered? Yes. Got enough negatives in there? Yeah, the problem is ACKs are unreliable as well, right? What if the ACK is dropped or the message is delayed? You end up with retransmission and duplication. Everybody clear on that piece? All right, so... Yeah, go ahead.
Like, what if the ACK time is ridiculously long, so you're just constantly sitting there just firing one packet off, and then,
If the ACK time is ridiculously long, yes, you will end up sending a bunch of packets. All right, and eventually what will happen is when the first ACK comes back, a good protocol like TCP will figure out that your latency is really long and will adapt to that. Okay, so your timeout, we're going to make for an adaptive timeout as well in this process. Okay, so how do we deal with duplication so we can put a sequence number? I wanted to show you the key here is that the sender has to keep a copy of unacked messages and the receiver tries to track for duplicates. And here's a very simple protocol where we use a single bit where there's a single bit sequence number and we put bit 0, we set the bit to 0, we send the packet off, we get ACK 0, we set the bit to 1 and so on. And what's good about this is the sender keeps the last message and the receiver tracks the sequence number of the last message received. And as a result, when you're sending packet 1, if it notices more packet 0s, then it can figure there's a duplicate. Okay. Now, of course, you think about this through, you'll see that the con of this is the very poor performance because we can only have one packet on the wire at a time. And in reality, what you really want is you want to have as many messages as will fill up the pipe between you and the destination and back. That's the optimal pipelining. Okay. So I think we're just about out of time here. So I just wanted to show you, not quite TCP before you leave, but here's a better windowing protocol. The idea is we allow ourselves to send up to n packets without an ACK to allow pipelining. And as we start getting the ACKs back, then we can send other ones. And the key idea here is we have to negotiate between A and B what the queue size is at the destination so that we never have more things in flight than will fit in memory. Okay? And the ACKs are basically helping us for reliability and ordering. And basically, if the packet gets garbled or dropped, the sender can send a timeout and so on and resend missing packets. All right, so next time, what we're actually going to talk about is we'll talk about TCP/IP, which is a much more sophisticated version than this. But before I close out, are there any questions on the simple acknowledgement idea? Multiple packets in flight. If an ACK comes back, that's if packet 4 never gets its ACK back, the sender can resend 4. So we're basically allowing ourselves to have as many sequence numbers as there are packets in flight. Okay? All right. So in conclusion, question. Go ahead.
What lecture did you cover at next semester?
Next one. Yeah. So in conclusion, we talked. The question was what lectures are included in the midterm, and I said the next one, up to the next one. So the network is a physical connection that allows two computers to communicate. We talked about broadcast networks, which are shared communication media, where all packets go to all members. We talked about point-to-point networks, which is a network in which every physical wire has only two computers. We talked about agreements between two parties, which are protocols. We talked about IP. We talked about the DNS system. We actually talked about a lot of things today. And the next time, we're going to talk about TCP/IP. We haven't gotten there yet, but I'm going to show you it's a better version of that acknowledgement protocol I just showed you. And then we have a bunch of really interesting things to do with networking, which we'll talk about next time. So have a great weekend. We will see you Monday.